The previous series on this channel has shown that the fundamental equation of quantum mechanics is not the Schrödinger equation, as one almost universally declares, but that of Paul Dirac, for the simple reason that the latter is relativistically invariant, while the former is not. See the links below for more details. Episode 4 of the series used the simplified form of the derivation according to Dirac himself. This involves the process of splitting quadratic expressions like the one shown into two linear terms, each of which can be used separately if the original expression ends with is 0, while making extensive use of matrix manipulation. As pointed out there, this manipulation is in first instance a purely mathematical one and has a certain amount of arbitrariness. Shown is a more explicit version of the end result, with the Pauli spin matrices clearly visible in it. Here an alternative route is followed, not to replace the original one, but to highlight the physics involved, which might be useful at some instance. This uses a lot of equations, but all of them are of the tell your grandmother type, for anyone with knowledge of mathematics at high school level. No spinners, SU2s, Clifford algebras come by. It is almost fundamental physics while having fun. The downside is the limited production facilities and capabilities of old-fashionedness, so the equations are gathered in lumps per slide, while reading some text in order to break the silence. The more visually oriented can put on their headphones. You should put them up for slides that do not contain any text. So here we go. These are the basics of the approach of de Broglie, but now in the form of differential equations. De Broglie's concepts are present in any form of quantum mechanics. All of them! Exclamation mark. Those who say otherwise are cheating. As soon as they use the operator definitions and relativistic invariance, see the earlier series. Now de Broglie also assumes an aspect of the oscillation that experiences a propagation delay, this is, that looks like a wave, and effectively applies a Lorentz transformation to it, which introduces the term linear in velocity, as also shown in the more streamlined Bergman version. This explicit introduction of a second wave function component is the first step beyond de Broglie. We now have his model in a first mathematical form. For the next step, some preparation is needed. Now we are ready for the next major step, whereby relativistic invariance has been included, and we can round things up. This is the major result. We fully got de Broglie's original ideas into mathematics by introducing more components to his oscillation and expressing its transformation properties into relations between these. What follows are merely repetitions of these same steps. This step may initially require some puzzling, but with taking alternate cases of zero momentum in the x and y direction, one quickly comes to this result. So there is one more repetition to go. And for those still listening, there is your Dirac equation. It officially still needs the step of substituting the operator definitions, but that is completely standard. But that doesn't look like my Dirac equation, I can hear you say. So you must have done something wrong. No, I did not. I strictly followed the rules. But you don't get my Dirac equation. Yes, but that's because Dirac didn't follow the rules. Here's what Dirac did in terms of our derivation. Simple, isn't it? Why didn't you do that earlier for the x direction? Which could be followed by another protest, like, yes, but Dirac didn't use this method at all. To which the answer is, yes, that is correct, he used matrices, but using these matrices is precisely the same as our algebraic approach. And the algebraic approach could at any time have been presented using Dirac-like matrices. Here's a part of a generalized version, where the resulting Q matrices are adimensional. And this is a possible set of matrices corresponding to the isotropic approach. But we didn't use this more systematic method, because we wanted to show a hidden danger in using abstract mathematics, one could easily miss something of importance for the physics behind it. In this case, what remained hidden is the fact that Dirac has treated the three spatial dimensions unequally by using a different method of splitting the quadratics for the y direction, to which he was seduced by the availability of the Pauli spin matrices, because that is in effect what happens with the combining of px and py using the imaginary unit number. You introduce the second polymatrix. In our algebraic approach, we only use the first and third one of these. So what are the consequences of all this for physics? That's a question that clearly goes beyond the scope of this video. To help with this question, it is followed by another one, which employs the more systematic approach using matrices. Meanwhile, one can ponder on the question what the different approach means for the meaning of spin in spacetime. Because of the Dirac equation, and especially its gamma matrices, one says that they reflect the properties of these fundamental concepts. Then what is the meaning of a different representation, more strictly based on the equality of the three spatial dimensions? These puzzles will be the subject of a follow-on video, which will be slightly more formalistic. So keep on watching and perhaps also have a look at how on this channel the interpretation problems of quantum mechanics have been solved using similar methodology.